Hello, my name is Daniil Chivilikhin, and today I'm presenting the work on evaluating the hardness of SAT instances using evolutionary optimization algorithms. This is joint work with Alexey Semenov, Artem Pavlenko, Ilya Otpuschennikov, Vladimir Ulyantsev, and Alexey Ignatiev. In SAT, we deal with Boolean formulas, which are built of Boolean variables, which can have positive and negative literals, and the formula is built of literals, braces, and logical connectors. Most often, we deal with formulas in conjunctive normal form. These are made of clauses, which are in turn disjunctions of literals, and the conjunctive normal form of a formula is a conjunction of clauses. The Pullian satisfiability problem in its simplest form is formulated as follows. Is a given Boolean formula in CNF satisfiable? SAT is well known to be NP-complete. Therefore, some SAT instances are very, very hard. And in some practical applications, it is important to be able to estimate the hardness of formulas prior to trying to solve them. What is known about hardness measures for SAT? Well, for some polynomial classes of formulas, such as 2CNF, Horn formulas, Shepard's class, there are known analytical measures. For other harder non-polynomial decidable formulas, for example, for family of pigeonhole principal formulas, there are known exponential bounds for such algorithms and decision procedures as CDCL, resolution, etc. But in general, there is no efficient way to assess the hardness of CNF formula with respect to an arbitrary SAT solver. What is known? Consider an arbitrarily complete CDCL SAT solver and an arbitrary CNF formula. The simplest way to assess the hardness of the formula is just to launch your SAT solver and wait. But due to different phenomena, for example, heavy tail behavior, this process may not terminate in any reasonable time. The other idea is to use strong backdoor sets. This idea was proposed in Int'l et al. That uses the strong backdoor sets that were described in Williams et al. Now we will introduce a strong backdoor set. Consider a set of Boolean variables x, an unsatisfiable CNF formula C over x, and an arbitrary subset B. Introduce the following notation. For the set of all assignments to variables from B, introduce an assignment beta, and introduce weakened CNF formula C beta slash B, which is derived from C by simply substituting the assignment beta of variables from B. A set B is called a strong backdoor set for formula C with respect to a polytime subsolver P if for any assignment beta from set B, the formula C beta B is reported by P to be unsatisfiable. And the idea proposed in Int'l et al. Is that we can use this to assess formula hardness. The results of Int'l et al. Lead us to the following definition of backdoor hardness for unsatisfiable formula C and polytime subsolver B, and an arbitrary strong backdoor set B. We can define the hardness of the formula with respect to this SBS and subsolver P as a total runtime of this subsolver P on all weakened formulas C beta B. And then we can define the backdoor hardness of the initial formula C with respect to the algorithm P as the minimal hardness for across all strong backdoor sets. How can we use it in practice? The algorithm for finding the minimum SBS, suggested in Williams et al., enumerates all sets B of size 1, 2, 3, etc. And for each set, it checks whether it is an SBS. And for that, it solves all weakened formulas C beta B for all assignments beta. And it's not hard to see that this algorithm is impractical if there is no small SBS. Moreover, it's only applicable for polynomial subsolver P, and in practice, we do not often use polynomial SAT solvers. So what can we do for an arbitrary complete SAT solver? In this work, we propose to extend this definition of backdoor hardness to decomposition hardness. And the extension lies in the fact that instead of polynomial subsolver P, we use an arbitrary deterministic complete SAT solver. and define the decomposition hardness analogously with that hardness. In this work, we propose this new hardness measure for arbitrary CNF formula C with respect to arbitrary set solver. And we also propose a practically applicable algorithm to seek the set B with minimal d-hardness. And this algorithm is based on an epsilon delta approximation of the hardness of a formula with respect to the set B and the set solver A, and an evolutionary optimization on Boolean hypercube. And we also demonstrate practical applicability of this approach on several families of set instances. To build this algorithm, we first introduce a probabilistic expression of this hardness measure mu BA. So with each set B, we connect a random variable CB, which for any assignment equals the running time of the set solver on a weekend formula C beta B. And it is not hard to show that we can connect this hardness measure with the expectation value of this random variable constructed in this way. Since we use a deterministic and complete set solver, we can safely assume that the expectation value of this variable is finite. Because of that, we can estimate the value of this hardness measure using Monte Carlo method. And in the paper, we prove the following theorem, that we can build an epsilon delta approximation of this hardness measure, which is expressed as shown in this red rectangle. And the theorem states that this expression is an epsilon delta approximation of this hardness measure when we select a sample size as stated in theorem. Of course, in practical applications, in practical implementation of this algorithm, we need to replace the expectation value and the variance with their statistical counterparts. And we do it by replacing the expectation value with the sample mean and the variance with unbiased sample variance. Now, we have a means to estimate the hardness of formula with respect to a set solver and an arbitrary set B. But we are interested in finding the set B associated to the minimal value of this hardness. The simplest way to do it would be to apply something like Williams' algorithm. But as we show further, it's not a very good idea. And in this work, we employ for this task evolutionary optimization algorithms. These are black box optimization algorithms that initialize solutions with some possibly random way, and then estimate their quality using something called a fitness function, and try to vary the solutions using mutation and recombination and selection. And this loop stops when we either reach some predefined goal or use up all computational resources. In evolutionary algorithms, we have to define the representation, the solution, the fitness function, the mutation operator, and the crossover operator. So in our case, the candidate solution is a subset of set of variables X. To represent this set, we use a Boolean string in which the if element corresponds to having or not having a particular variable in the set. So for example, if we have 5 variables and the set B contains 3 variables, and this would be the representation. Our fitness function accepts as input the representation of some set B and tries to measure the hardness of the considered formula C with respect to the set B and the set solver A. And for that, it uses the Monte Carlo method. So we first build a random sample of size n of possible assignments of variables from set B. And for each assignment beta, we measure the value of the random variable, corresponding random variable, by running the set solver on the formulas C beta B. And then we aggregate this in the fitness function, which is the following form. The mutation operator operates on the representation of the set and basically either removes or adds some variable to the set. In the simplest form, it flips each bit with probability 1 divided by n, where n is the number of variables. So for example, if the algorithm selected these 2 bits to flip, then the resulting solution will be the following. The genetic algorithm, which we use, is using the simplest 2-point crossover operator, which selects some interval in the string and flips these subsequences, producing 2 child solutions. So let us describe the simplest form of evolutionary algorithm that we use. It's called the 1+1 evolutionary algorithm. We start from the set that contains all variables. Notice that for this set, we can always efficiently estimate the value of the fitness function. So first, we estimate the value of the fitness function for the whole set. And then while we have some computational resources left, we try to mutate this solution, estimate its fitness function value, and if it decreased, then we substitute the current best solution with the current one. For example, consider the following history of evolutionary algorithms. So here's iteration number, the size of the set, the representation of the set, and the value of the fitness function. So first, the algorithm always tries to remove some bits to remove some variables from the set, and thus decreasing the fitness function value, but not always. For example, here we had 3 variables, and we transferred to 4 variables, but with the smaller value of fitness function. And then after some iterations, we used up all computational resources and returned this set as the result. In experiments, we use more complicated algorithms, so a standard genetic algorithm using imitation crossover, and a fast genetic algorithm, which does not use crossover, but uses a little different mutation operator. We implemented our d-hardness approach in a framework EvoGuess, which is written in Python, hosted on GitHub, and it uses PySat for interfacing with SAT-solver. In our experiments, we used 2 classes of benchmark tests. First are crafted tests generated by SGEN. The other class of tests are equivalence checking tests, trying to prove equivalence of algorithms expressed as Boolean circuits. Here, the tests are constructed in such a way that the Semenov formula is unsatisfiable if and only if the algorithms are equivalent. And here we considered pairs of sorting algorithms that sort any d-L-bit numbers. So these are the notations of the pairs of algorithms considered. We use the following experimental setup. To measure the hardness of launching a SAT-solving algorithm on some SAT formula, we used not the time, but the number of unit propagations for the reason of reproducibility and the ability to use multiple platforms to get the same results. And we considered SAT solvers glucose-3 and catechol. The experiment was divided in 2 parts. The first was to search for a set B with minimal d-hardness. And for this, we used up to 12 hours of wall clock time, using up to 5 nodes of a cluster. And then, having already found set B, we solved all weekend subformulas defined by the set on single thread and multi-thread. So, for example, here we have 8 variables in our Semenov formula. We have some 3 variables in the set B. We generate all weekend formulas by substituting these assignments, and then solve all these weekend subformulas. First, we want to compare the results with using Williams algorithm, but with non-polynomial subsolver to search for our sets B with the d-hardness. And we considered one of the equivalence checking formulas and built all sets B of size 1, 2, and 3. This took up several days of one cluster node. So here the box plots correspond to all sets B found by analog of Williams algorithm, and the dots correspond to sets found by our evolutionary approach. We can see that the results found by our algorithms are quite close to global minimum of this hardness found by Williams algorithm, but much faster. Here we see results for different Semenov forms. For each set B, we calculated the so-called decomposition rate. It's the exact value of the hardness for this set B divided by the time used to solve for the initial formula with the set solver. As we see, often this decomposition rate is smaller than 1, indicating that actually solving all weakened subformulas defined by the set B is cheaper than solving the initial subform. This plot illustrates the behavior of the epsilon delta algorithm. In practice, when the value of epsilon exceeds the a priori given bound, we try to increase it by a factor of 2, 4, or 8. And this plot illustrates these different strategies. So we see that they allow keeping epsilon smaller than 0.1 most of the time during the search. And most importantly, when the set becomes small enough, we switch from Monte Carlo estimation of d-hardness to its exact computation, because we can just solve all weakened subformulas, thus giving us exact accuracy, epsilon equals 0. These plots also illustrate d-hardness estimation accuracy. So we considered several sets B found during one search. And this plot, this line in the middle illustrates the exact value of d-hardness, while the box plots correspond to several measurements of d-hardness measured with n equals 100th of total number of subproblems. And we see that this number actually is quite good and provides quite a good estimation accuracy, plus minus 10%. And the difference in these plots is that the top one measures hardness in unit propagation number, and the bottom one in time. And we see that they correlate not exactly, but quite substantially. This table shows results on solving all weakened subformulas defined by the set B on multiple threads. And here we calculate the speed up, but it's not very classical. So here the speed up is calculated as the number of unit propagations used by the set solver to solve the original Semenov formula, and divided by the maximum number of UPs used by all threads. So divided by the resources used by the slowest thread. What's interesting here is that for several formulas and several more also, we can see that the speed up measured in this way is linear or superlinear, indicating quite a good efficiency gain. So in conclusion, in this work, we have proposed hardness notion for unsatisfiable subformulas that can be used with respect to an arbitrary deterministic subsolver, and proposed a practical epsilon delta approximation algorithm to estimate it, and demonstrated the effectiveness of this algorithm in several families of subformulas. In the future, it would be interesting to apply our results to estimate the usefulness of cubes and cube and conqueror, or to extend the proposed ideas to existing algorithms based on strictly stronger proof systems and resolution, such as cutting planes and dual rail based max SAP. So we are grateful for the grants awarded to us in this work, And thank you very much. Feel free to reach me on Telegram or on email.